I want to take a little closer look at how we decide where this line sits so that it becomes a line of best fit. Right? As we eyeball this, there's probably a couple different ways we could draw that line. So, how does the computer decide which one really is the best fit? So, it turns out that this is related to the name of this line, which is the least squares regression line. You probably heard me say that a couple of times in the lecture. And so, that name actually tells us how they're finding where the line goes. So, I have a data set here with 5 points A, B, C, D, and E. Some of them are above the line, some are below the line. And so in order to figure out kind of where this line of best fit goes, from each point, we drop a straight line down to our line of best fit. So I have one line here. From letter B, I drop a line straight down. Same thing from letter C. So I'm just dropping lines from the point either straight down or up. So you could also go up to that line of best fit. And then what we do is we measure that distance and we square it. So when we square it, it actually creates an area here. It's a squaring is not just multiplying it by itself, but we're actually kind of coming up with this idea of area by squaring it. And then we add up the areas of all of these squares. And so we're looking for the smallest total area. So here's one line. If we move the line somewhere else, the areas are going to change a little bit. So we can calculate all of those and add those up. So then we would choose the one that had the smallest combined total area. So that's what that least in the least squares means, is we're looking for the lowest or the smallest amount of area when we use this squaring process. All right, so hopefully this gives you a little bit better idea of kind of why we call it a least squares line and how we know that this is really going to be a line of good fit. Right. And then one last thing that goes with this is a statement that you probably have heard thrown around before, which is correlation does not equal causation. So what that means is just because I plot two variables on the same scatter plot, they appear to have a fairly strong relationship, doesn't mean that one of these is causing the other one. So if we look at our ice cream sales example, it is probably reasonable to think that in general, as the temperature increases, it is going to cause our ice cream sales to increase as well, at least for a certain amount of temperature values, right? So that's probably fairly realistic to think that maybe there is some cause and effect there. But what if we did something similar? So this is the number of sunglasses sold versus the ice cream sales. So if we try to apply that same logic, does it make sense to say that as the number of sunglasses sold increases, it causes ice cream sales to increase? The answer to that is no. We don't think that just because sunglasses are being sold, it's going to cause the sunglasses themselves cause the ice cream sales. What's really going on under the surface is there's another variable that isn't on this graph, and that variable is the temperature. So when it's hot and sunny out, people are going to buy sunglasses, people are going to buy ice cream. And so that's really what's driving this relationship here. So just because I put two variables on here and it makes something that looks linear and fairly strong, it doesn't mean that it's a cause and effect. It just means that these two variables are somehow behaving together. And it could be cause and effect, or it could be something else going on underneath the surface. And that thing underneath the surface actually has a name called a lurking variable, right? So it's just kind of hiding there underneath of what we actually have going on under the graph, and that's really causing what we're seeing. So that phrase, correlation does not equal causation, means just because we plot things and they look good together doesn't mean that it's actually cause and effect.